Carbohydrates are the main macronutrient, contribute to blood sugar spikes, to cause and worsen insulin resistance.
There has been a lot of work published in the recent years to understand the underlying pathologies of insulin resistance. And to fully understand insulin resistance, we should first understand the insulin signaling cascade. This is the insulin receptor. That protein on the outside is considered the alpha subunit, and the protein on the inside is the beta subunit. Insulin comes along and binds to the alpha subunit. This causes these two subunits to bond to one another, and this process is referred to as dimerization. They can then go through a process called autophosphorylation, which is very simple. The proteins inside of our cells that are able to add phosphates to other molecules are called kinases. Lucky for us, the beta subunit of the insulin receptor is also a kinase. This process is referred to as dimerization. So when the two beta subunits of the insulin receptor will dimerize with one another, they can essentially add phosphates to each other. And these phosphate groups essentially act as energy to either inactivate or activate specific proteins inside of our cells, which you will see in a moment. This allows another protein inside the cell called IRS to bind to these phosphate groups. Along with this IRS comes two other proteins called P85 and P110. When these two proteins are attached to one another, we also refer to this protein complex as PI3K. This complex can then travel inside of the cell across to another molecule embedded in the membrane called PIP2. That protein will donate a phosphate to PIP2, converting it into PIP3. Once this occurs, another molecule called PDK1 can bind to PIP3. And PDK1 can then activate a small protein inside of our cell called AKT. Stick with me here because we're almost done. AKT can go around and add phosphates to a bunch of other proteins inside of our cells. Specifically, it will add a phosphate to a protein called AS160. Under normal conditions, AS160 is bound to this vesicle. These purple proteins are called GLUT4 transporters, and they are molecules that can take glucose from our bloodstream and transport it into our cells. But when this vesicle is bound to this protein, the vesicle is unable to embed itself into the membrane. But lucky for us, when AKT binds to AS160, it inactivates the protein, allowing those GLUT4 vesicles to bind to the membrane and begin allowing glucose into our cells. And this is how insulin lowers our blood glucose. Insulin resistance. So let's discuss what we do know about insulin resistance. What we know is that insulin resistance starts in the muscles and in the liver, before spreading to other tissues such as the kidney and the adipose tissue. There are two main things that drive insulin resistance. The first is the accumulation of both fatty acids and diacylglycerols inside of our cells, which inhibits IRS1 from associating with PI3 kinase, which hopefully you remember is the very first step in insulin signaling. Obesity is the main contributor to the accumulation of free fatty acids and diacylglycerols. This is because obese people have increased lipolysis, because the excess adipose tissue in their liver and in their muscles begins leaking fatty acids. The second, likely most important driver of insulin resistance is physical inactivity, because exercise of all types can correct the imbalance between fatty acid uptake and fatty acid oxidation. And exercise, even without weight loss, can reduce insulin resistance. But this insulin resistance will come back to baseline if the overfat individual does not lose weight and does not continue with the exercise. Additionally, to say that carbohydrates drive insulin resistance is simply unfounded. High carbohydrate overfeeding results in changes compatible with increased insulin sensitivity. But it also appears that high fat overfeeding reduces insulin sensitivity. And as much as many people do not want to talk about it, a low carbohydrate diet negatively affects glucose tolerance in the liver and the muscles, specifically a high saturated fat diet. This is considered to be adaptive or physiologic insulin resistance, because when the liver and the muscles become insulin resistant, they reduce their uptake of glucose, which can spare glucose for the regions of the brain that require glucose to function. So this may not necessarily be a negative thing in the context of a high-fat, low-carbohydrate diet, but it is important to understand this fact. Additionally, glucocorticoids such as cortisol and catecholamines such as adrenaline increase the release of free fatty acids, which is the underlying reason in which catecholamines and cortisol increase insulin resistance. The second pathway that drives insulin resistance is inflammatory cytokines, specifically cytokines such as interleukins, because they can activate a specific protein inside of our cell called SOC-S3. And just like the accumulation of fatty acids and diacylglycerols, this protein can inhibit the initial step in insulin signaling by inhibiting IRS1. This line with the flat N denotes an inhibitory effect. So insulin resistance can be worsened by stress, fever, illness, and infection, including a periodontal or tooth infection. There are a few other minor contributors to insulin resistance, such as iron overload, micronutrient deficiencies, or excessive exposure to things like heavy metals. But to say that carbohydrates drive insulin resistance is simply short-sighted.